But the intuition is that knowing these 5 conserved quantities is going to tell me a bit about what my prediction should be. And so it's kind of free information that I get to know.
Hello there. Today we'll look at Noether Networks, Meta-Learning Useful Conserved Quantities by Ferran Alet and Dylan Doblar and others. This is another one of the with the authors installations, videos, whatever, where I just discuss the paper briefly right now, and then we'll jump into an interview with one of the first authors, with Ferran, and we'll go through the paper together. And I think Ferran can explain this so much better than I can, and I'm also able to ask some of my dumb questions. So this was a lot of fun, and I definitely invite you to stick around. If you already know a little bit what the paper is about, feel free to skip ahead. If you don't know what the paper is about, the paper essentially deals with neural networks that predict dynamical systems, and in these dynamical systems, very often there are these conserved quantities that are part of it. For example, in a physical system, energy is conserved, momentum is conserved, and things like this. And under this constraint, you can build in this constraint into the predictive neural network so that the neural network does a better job. And they build these Noether networks in order to dynamically learn these conserved quantities and then adjust at runtime during forward propagation, tailor the loss to conserve these quantities. And I think that's really cool. It's different, and yeah, that's what I like about it. So pretty brief introduction. This paper obviously is named after Noether's theorem, which essentially, they say here, loosely states the following. For every continuous symmetry property of a dynamical system, there is a corresponding quantity whose value is conserved in time. For example, they say a system of planets interacting via gravity. The system is translation invariant in all 3 cardinal directions. Noether's theorem asserts that there must be a conserved quantity for each of these symmetries. In this case, linear momentum is conserved. So the symmetry in space as translations is accompanied by a conserved quantity, which is linear momentum. Now, we don't always obviously know these quantities, and they're not always super explicit, and they're not always exact. So what we are going to be dealing with here is predictions of dynamical systems. And the example here is the prediction of a video of like a physical interaction. So this is a thing here on an inclined plane. It sort of slides down and then collides with this other thing right here. And the goal is to predict the next frames of this video. Now, we could just build a neural network to predict these things frame by frame by frame. And that would go certainly well if we had a lot of data. However, if we don't have a lot of data, what we need to do is we need to build in inductive biases. And the inductive biases, what people usually do is they build in these symmetries directly. For example, they build in the physical laws, they know how the world works, and they say, you know, whether I translate it to the left or to the right, it doesn't really matter, and so on. But building in these symmetries, and I think we know this from geometric deep learning, building in these symmetries is very powerful, but it can also be cumbersome because you have to define them beforehand. This paper goes ahead and says, you know, what's a lot easier than building in symmetries directly is building in a constraint to conserve a given quantity. And that is a lot easier, and there's a potential that you can actually learn it from data. And with Noether's theorem, we know that the two things are equivalent. So if a system conserves a quantity, it essentially encodes a symmetry in the system. So what do? This is the very high-level overview over these networks. So this entire thing here is one forward propagation. We take the original frame, we put it through a forward predicting neural network, which is this F theta right here. This is a network that simply forward predicts frames as I said initially. So we forward predict, forward predict, forward predict. This gives us an initial set of outputs right here, these X tilde. Now, these are going to be pretty bad not pretty bad, but if we don't have a lot of data to learn from, we don't expect them to be particularly good, and that's the regime we are here. What we do then is we're trying to adjust this f thing right here in the moment. So during the forward propagation, we're going to update our predicting neural network by this neutral loss. So we're going to do an update, a temporary update to the weights of the F network. And we're going to do this into direction of this neutral loss. So you can see here, we have these networks G lying around, and G is always the same network. So what we're going to do is we're going to feed each frame that we predicted through G, and G always being the same network, it will output the same thing. And now, obviously, if given that how I made this introduction, you might already have guessed that G is the part that predicts the quantity to be preserved. So what we want to do is we want to put all these things through G, and then we want to, these will give us a bunch of outputs, right? G here and here and here and here will output some things, and the things can either be a number or an entire vector, right? An embedding vector. So essentially G takes this thing right here, it actually takes 2 consecutive frames and embeds it into some space. And now ideally all these G's would output the same thing, which would mean that we have conserved some quantity and therefore encoded some symmetry. However, initially these G's are not going to output the same thing, so we are going to attempt to change the f function such that the G's output more the same thing. There is a loss involved right here. This is the neutral loss, they call it, and it is defined down here. So you can see all this really is it's either defined in one of 2 ways. Either you take the difference between the G function of the initial frame and the frame at time point t, and you calculate the difference, or you calculate the difference between consecutive frames. In either way, since you sum across all the frames, this means that all the outputs of the G network should approximately be the same. Now, what do you do with this information? Again, we're still during one forward propagation. So what do you do with this information? You calculate this Noether loss, which is one we just described, and then, sorry for skipping around so much, you're going to do one update step. So these are the parameters of the F network. We're going to do one update step into the direction of the gradient. It's the direction of the gradient with respect to the parameters of the F network. So this is the forward predicting network. So essentially we are saying, how do I need to update my forward predicting network such that the frames that it outputs, the frames that it predicts in the future, make it such that the G functions of all of these frames are more similar to each other or more similar to the G function of that first frame, right? So we're going to, in time, update the F function right here. And after that, we're going to forward propagate again with this new F function and thereby obtain our final prediction. This is like an inner optimization that we do during forward propagation. I find this to be pretty cool. Now they just do one gradient step, obviously. Otherwise, you could do a lot of things, and you could like program in Adam and Adagrad, not only one like gradient step, which is one SGD step essentially, but even with one step, that is good enough. So again, here is the entire training procedure in an algorithm. You can see that, let's start down here. They start with randomly initialized weights. These weights here are for the G network. These weights are for the F network. They sample batches. For each batch, they predict the sequence. Now, the sequence prediction is this entire thing we just looked at. So the sequence prediction is, I'm going to start at the initial frames. I'm going to use the F, the original F, the one I currently have, unconditional, let's say, to forward predict all of the frames once. Then I'm going to put all of these predictions here into this Noether loss. I'm going to calculate the gradient. How do I need to update this f for this particular data point to make the g functions output the more similar things? I'm going to obtain new parameters. Again, these are just temporary parameters. I'm going to use these temporary parameters here to do another round of forward prediction, which gives me my final estimate. I could probably repeat this again, or I could do multiple steps right here. I could probably do a lot of things, but this is sort of the simplest case. And then I'll return these. What do I do with them? You can see right here, this is my output. Now I'm going to input these things into what's called the task loss. And the task loss in our case here is just the video prediction loss. So that's going to be some L2 distance between the frames that I output and the frames that actually, so that these are the output frames, these are the frames that are actually in the video. And then I'm going to just run backprop on that. So update the parameters of both G and F on the task loss. So what does it mean? G is going to be updated such that if I do this whole sequence again, if I do the whole sequence of predicting, then tailoring my loss to G, right? I tailor my loss to the G function. G is going to be updated such that next time, if I tailor my loss to it, it's going to lead to a better outcome overall. And F is going to be updated similarly. It's going to be updated such that, well, next time, if I do this whole procedure of first predicting these, which I'm going to use the parameters, then updating the parameters, and then, then updating the parameters using G, and then predicting again, I update my F such that this whole procedure will result in a better loss. Now this is, I think this is the magic of our backpropagation frameworks, that we can even think of these types of things, because, I mean, behold, actually writing this down and implementing the backwards pass here yourself. That'd be crazy. So this is the entire algorithm right here. Now again, given that there are, as you can see, some hyperparameters here, such as the learning rates, they only do one gradient step, as we mentioned. So this isn't an exact enforcement of that constraint, right? This is only an approximate enforcement. Essentially the only condition, the only additional constraint that we introduce here is this requirement that the G function is the same G function on all the forward predicted things. And that is our knowledge that we are dealing with a dynamical system, and in this dynamical system, some quantities should be preserved. The way we build the losses means that G can simply output a constant value, otherwise it would not be useful to the loss, right? But also the way we build the loss means that it is not an exact constraint, like we would build this into the architecture that a quantity must be conserved. So it's able to deal with, real world data, such as this video, where even sometimes like a hand may come in, there's friction and so on. It's not an exactly conserving system, right? And the way we do this in the moment, in the forward pass update using this Noether loss, that means that I can now tailor whatever, like I can tailor the inductive bias for this particular sample. So I can learn, it's kind of meta learning thing, right? What I learn is how to, in the moment, adjust my loss function to this particular sample of data. Now, as I said, obviously, if you had more data and all, maybe you wouldn't need this, but it does help a lot in their experiments in these regimes where you do not have a lot of data. They have a theoretical section right here where they have a reduced case and show that it can be useful to impose these constraints. Then they have a bunch of experimental settings. Among other things, they don't only do what I just said with the video prediction, but they also do a prediction where not everything is a neural network. So where the things they predict are actual physical quantities, and they do it using symbolic regression. And this is the same method, except it's not neural networks, it's symbolic regression. And what that does is it comes up with these equations, for example, for the ideal pendulum. As you can see, these equations are insanely close, like they recover the correct equations. And these are symbolic regressions. So you didn't only have to come up with the number right here. The network had to come up, not the network, the system had to come up with the entire equation, given some basic building blocks of variables, and you can square stuff and you can take the cosine of stuff. So these experiments show that the method can indeed recover physical quantities that are conserved if you present them with a scenario where this is the case. And they use either ideal scenarios, so ideal data generation, but they also use real-world data from pendulums, where obviously you have energy dissipating. And then you can compare. So here, I believe they do compare with what they say is a baseline. So as that predicts into the future, the longer prediction they do, the worse that gets. Or I guess the losses over here, you can see that. But then also the Hamiltonian neural networks, which enforce exact constraints. They enforce the quantities to be preserved exactly. If you face them with real-world data, you can see right here, the quantities aren't changed at all, yet the loss still goes up because the quantity isn't actually conserved in the real data. And the Noether networks do follow the ground truth data much more closely because they can model also inexact constraints and not super strict enforcement of these constraints, which is what I think we need in real world data. They do have a bunch of other experiments, especially, as I said, also video prediction, where they do outperform various baselines. They investigate where the network pays attention to and whether or not you can actually move or do a lot more inner iteration steps than just one, because we just did one inner iteration steps. There is no reason why this should remain at one. And here they show that even though they only trained with one, at inference time they can actually take a bunch more and the outer loss will still go down. So it all validates a little bit of the reasoning behind the method. I don't want to take up too much of your time right here because I want to jump into the interview. Let me know what you think of these more interviewee style paper reviews. I quite enjoyed the interview, and I do think it's pretty useful to have the authors there because they can correct me pretty instantly. All right, see you over there. Okay, cool. Hi, everyone. Today I have with me Ferran Alet, who is one of the primary authors of the Noether Networks paper, and here to discuss with us probably a little bit about the intrinsics of the paper, and maybe also for me personally, because the paper is very technical. It's a new field for me as well, connecting physics to machine learning, building all of this into neural networks. There's also a bit of symbolic regression in there. So I feel a lot of things are coming together here. I found the paper pretty cool and it's new, and that's what's interesting. So Ferran, thank you very much for being here.
Yeah, thanks for the invitation. Wonderful to be here.
Thanks. So your paper deals with, do you call it Noether networks? How do you pronounce?
I pronounce it Noether Networks, but I think I'm not German, so I'm not sure I'm pronouncing it properly.
I'm not a German either, but I think that the author was called Noether. Yeah.
So you're pronouncing it more properly than I am, I think.
Maybe. But essentially, could you give us maybe just first an insight, where does the name, because the name is kind of distinct, right? Because there is the Noether theorem. Yeah. What does the Noether theorem say in general?
Yeah. So the Noether theorem was kind of the inspiration for our work, and the intuition is that for every symmetry of a dynamical system, there is a certain conservation law that's going to apply to that system. So for instance, imagine you have a planetary system of planets moving around the physics laws don't change from today to tomorrow. That means that there's a time symmetry of the system. And here, Noether's theorem tells you, oh, if there is a symmetry here, that means that there must be a quantity that's conserved over time. And in this case, for time symmetry, there is energy that's being conserved. So we use that as a motivation, not that the technical details, more like the higher level message of the theorem to build a new machine learning model. And the intuition is that in machine learning, symmetries are one of the core ways in which we've improved data efficiency and model performance. And so it would be very cool if we could kind of automatically learn some of these symmetries. But symmetries are kind of hard to quantify and get a hold of computationally. And the intuition is that they talk about kind of counterfactuals and kind of global, in the sense that when I was telling you about this time symmetry, I was saying, if I were to look at the planetary system tomorrow, the laws of physics would be the same. But I don't have access to the data for tomorrow. It's a kind of counterfactual, so the model cannot handle this. Instead, conserved quantities can be directly measured. I can check, oh, this quantity, which I will call energy, is being conserved on my actual data. And that makes it very easy to quantify.
Yeah, we've heard I think in the recent past even, a lot of people attempting to get more out of symmetries out of neural network with, I'm thinking of like group convolutional neural networks and so on that try to actively build in symmetries into neural networks. Yeah. But it seems like they can only do that in situations where they know the symmetry that will appear. They already know a molecule. Doesn't matter which way I look at it, right? So I can directly build that in. But your reasoning is that because assessing conserved quantities is an easier task than assessing symmetries, it might be possible to learn the conserved quantities dynamically, actually learn them from data. Is that approximately correct?
Yes, exactly. And the theorem is the motivation, because it tells us that conserved quantities are kind of on the same level of powerful as symmetries for dynamical systems in particular. If you're doing image classification, that does not apply, because image classification is not a dynamical system. But that's the intuition, yes.
And you even have some slack in there. You discuss, it doesn't even have to be absolutely conserved quantity. It doesn't have to be an absolute symmetry that we deal with. By learning it from data, we can even handle approximate symmetries. Is that about right?
That's another thing that may be a bit different from our work than other works, which is that some symmetries are only approximately conserved, or conserved quantities are only approximately conserved. So for instance, if you have a dissipative system, like in the real world, there's friction, and so you actually lose energy. If you don't consider the entire system, you usually have small losses. So in this case, you would like to say, oh, energy is conserved, but not quite. So it's fine if your prediction doesn't fully conserve energy. But knowing about energy conservation maybe helps you with the overall prediction.
And maybe I want to get to sort of a little bit of an example of where, so people can imagine this a little bit more. Now, I only have a mouse here because I forgot the iPad because I'm stupid, but maybe we can give the small example of a pendulum, right? Mm-hmm. So here's a pendulum, it hangs here, and it sort of gets down here, and here is the little ball. And the pendulum is accurately described by, I think, the angle right here, that it's sort of off the main axis, and also its momentum. Let's say it swings in this direction with a certain speed. And this describes the pendulum. Now, your model focuses on predicting the future, let's say, or at least from what I can tell. So what your model would be able to do is it would be able to predict the next time step right here, right? Then it's a bit here. It's a little bit more up to the left, right? Mm-hmm. So it's a little bit more up, and then it's even more up over here, and then it swings back, and so on. It swings back over. Now, can you explain to us what is the symmetry here, and what are the conserved quantities?
Yeah, so in this case, for the pendulum, we know that if we were to swing the pendulum now and 10 minutes from now, the physics wouldn't change. And so we know that there's a time symmetry. And so in this case, we would say, there's a time symmetry, and then another theorem would tell us, energy is conserved. So in this case, energy is a mixture of the kinetic energy, which is how much movement there is, and the more movement, the more energy, and potential energy, which in this case is because of gravity. So a combination of these must be conserved. We don't know exactly how, which formula, and that's what we're going to automatically discover.
I see. And the original approach, I think, would just be that here, this arrow, I parameterize this with some neural network, right? I just say, here, I plug a neural network, I predict the next time step, and the next time step, and the next time step. And that it will maybe work, right? But it will, let's say, it will only implicitly make use. It will not actually make use of the fact that something is conserved.
Exactly.
So you go ahead and you say, since this is a dynamical system, we know more about the system, we can impose additional constraints. And the additional constraints right here, if I see this correctly, essentially at every time step, you say, I want to build a neural network that's always going to be the same neural network that takes a state, let's say the pendulum in this state, and predicts a quantity. Let's call that, no, G is the name of the network. Let's call the quantity, I don't know, alpha. And I want to use that same neural network in all the different states that I find this thing in, and it always needs to predict the same thing, right? Since it needs to figure out a quantity that is conserved.
Exactly.
And now it is if I just train a neural network to always predict the same number right here, I would just end up with a neural network that is predicting some kind of a constant, right?
Yeah, exactly.
So your method figures out how do I need to build, first of all, this predictive neural network to predict this conserved quantity such that it actually predicts something useful. But then also, how do I make this network right here actually use the fact that this other network predicts common quantities, right?
Yeah, exactly. So that's why the name, the word useful in our title, because there is many conserved quantities that are kind of not useful, and so we want to find those that are helpful for final loss. So in machine learning, we usually care about some performance, whatever it is, and so that's exactly what that our objective just cares about that, and the useful quantities are just a proxy, an intermediate thing for getting us to better performance.
Yeah, and so here you have this main diagram. I think that would be considered the main diagram describing your method. And this is on a task that is a video prediction task, and it's about sliding something down an incline. Could you maybe describe what the task here is?
Yes.
The frames are a bit low resolution. So
yes. So this is the Physics 101 dataset from Josh Tenenbaum's group. I think Jejun was the first author, and they have a collection of videos. And in this case, they have a hand dropping an object passively, like it just lets it drop down, and the object falls down. And there's a second object at the end of the ramp. They collide, and then the other one, sometimes depending on the masses and the friction and whatnot, the dynamics are kind of can change. So that's the data set.
And so that there are multiple videos,
yes,
and it's always different objects, or
like some objects could be common between videos, but there's lots of objects, so it's not always the same object, and that's kind of the point, the fact that it can vary. So one nice thing about the Noether networks is that they can deal with raw video. So some usually conserved quantities, you get them from kind of state data. Like when we were talking about the pendulum, it's kind of you have the exact position of the pendulum, you have the momentum of the pendulum, you don't have a pixel video of the pendulum. And here, because we deal with neural networks that predict the conserved quantities, you can hopefully get conserved quantities from video.
Yeah. So here the diagram shows a little bit of what you are trying to do, but also what you're trying to avoid. So the bottom path right here, if I see this correctly, that would be if I did nothing else except the bottom path, I would build this neural network to just predict sort of the future time steps. And that often turns out poorly. So I don't know, this is quite a pixelish mess, but it's sort of all of a sudden there are like 3 objects instead of 2, and the one is kind of gone or split up, and it's a bit of a mess. And you attribute this to the fact that it's just a video prediction, or?
Yeah, well, in this case, to analyze it and to make the problem challenging, we made like there was very few data. In general, you can it's all about, like, symmetries and inductive biases are going to be most useful when the problem is hard and then there's like less data. So in this case, there was few amounts of videos, and also because video prediction is pretty long. So at the very few, like the beginning of the frames, like the first few frames, there was not that much mistakes. But when you go very far into the future, then it's much harder. So those 2 problems, lack of data and the fact that you go a lot into the future.
Your method is, and you also have an algorithm described somewhere. It's a bit of it's a algorithm that is, right here. It's an algorithm that has multiple steps in it. And one special part is that you have this sort of inner optimization loop right here. Now, I want to maybe go back to the diagram and let's walk through it once before we take a look at the formulas and all. We can walk through it once. So the first thing that happens, if I understand correctly, is you take your first input and you do exactly what we just said. You run it through a forward prediction neural network that just tries to predict the future, just plain by itself. Right. So this has a bit of a default thing, but now you try to improve that, and this is the entire thing we're describing right now. That is one forward pass through your system. So you would take every single prediction that you made and you would feed it through this G network right here. And this G network is, you call it an embedding network. That is the thing ultimately that's trying to predict a conserved quantity. Right? But it's not necessarily just outputting one number. It's outputting an entire vector.
Yes.
So it's outputting an embedding vector, and the goal obviously is that for all of these inputs, it should output the same embedding vector.
Exactly.
But this is going to be, let's say, trained such that across the data set it works well. So maybe, for this video sequence, it's going to predict approximately the vector A for all the frames, if it works well. And for another sequence with 2 different objects that obviously have a different total energy or so, it might predict a different embedding vector.
Exactly.
But all the same across the video sequence. Okay, so this is how we can imagine you train this G network to sort of predict whatever is special about this particular data point, but inside of the data point conserved among all the frames.
Exactly, because if it was the same A for everyone, then you would get the issue that you mentioned at the beginning, then it's a useless conserved quantity.
So it's almost like a bit of a description of the scene as such, right? That makes the video predictor's life easier if you have sort of this global description. So the intuition, I think, is, let's think about when if the network G was very good at predicting the conserved quantities and perfectly told you, these 5 quantities, I know for certain that they're going to be conserved. Then we'll see the next step. We haven't gone through it yet, but the intuition is that knowing these 5 conserved quantities is going to tell me a bit about what my prediction should be. And so it's kind of free information that I get to know about constraints. So it's kind of an unsupervised loss that I have access at test time. It restricts what you can output, right? Because ideally the F network should only output whatever the G network says is the same, right? If the F network can only output things that the G network will embed to the same place in the embedding space or a similar place.
Yes, there's, just to be 100% precise, there's lots of images that could make the network G happy because it only constrains like a few dimensions. But it has to make the network G say, this is approximately what you had at the beginning.
Okay. And so that comes in the next step. So here, what you do, you take the input again and you route it through this F network again, but now this F network is not like a free-form predictor, but it actually has somehow the notion of this information that the G network output out of the initial sequence again. And you do this in a very special way in that you actually take the parameters of F and you update them on the fly.
Yes.
You update them so this is within a forward pass. You actually update the parameters into the direction of the gradient of G.
Exactly. Yes.
Yeah. Sorry. This is, I think that it takes it. Yeah. So here you have this Noether loss.
Yes. Exactly.
Which you maybe want to talk about this briefly?
Yes. So about the Noether loss? Yeah, sure. So the Noether loss essentially is telling you should conserve G. You know for a fact that so there's two ways of conserving G. They're roughly equivalent if you fully impose them. If you don't fully impose them, they're not fully equivalent. That's why we put the approximate sign. So let's look at the term A here. It's basically saying, you should conserve G, and so it should be, all of them should be equal to what G was telling you for the input X naught. So if you make the embedding of your prediction, note that the X sub T has kind of a tilde on top of it. So your prediction for XT should have the same conserved quantities as your input. And that's what the first term is, and just an MSE over this neural embedding. The second one is very similar. Sometimes it's a bit more useful, more stable, because instead of comparing to the very beginning, you compare to the previous time step, you have a more immediate signal, and you basically say you should conserve it. Every time you apply F, you should conserve G. So that's another basically imposing conservation. And
now we update theta, and theta are the parameters of F, right?
Exactly.
Theta are the parameters of F. We update these on the fly, and I suppose that we just do this, in the moment, and for the next data point, we go back to the sort of original parameters,
yes,
and do this again. So this is sort of an on-the-fly update for, a temporary update of these parameters into the direction of this quantity right here. So this is the gradient of exactly the loss that we just discussed with respect to the parameters of F. So essentially it says what parameters would make F more apt at fulfilling this loss, which essentially means that how do we need to change F such that these forward predictions make the G conservation happier?
Exactly. So this is some previous work of ours, which we call tailoring. And the idea of tailoring is just because of what you said, that the fact that the adaptation is customized for each individual data point. And the idea there was a general way of encoding inductive biases with unsupervised auxiliary losses. So auxiliary losses in general, you say, for instance, one thing we could say is, why not we add energy conservation when we train? Sometimes auxiliary losses would say, okay, I train for good predictions and I train for energy conservation at training time. But if you do that, you're not going to enforce energy conservation at test time. Because at test time, you're going to have a generalization gap in energy conservation. But energy conservation or any type of conservation or any auxiliary loss can be checked before making the prediction at test time or at training time. Inside the prediction function, I can first make my prediction and see, okay, do I like it? Does my auxiliary loss, does my unsupervised loss like this prediction? And if not, I can take a gradient step or multiple gradient steps to improve my unsupervised loss, in this case, the conservation loss. And so this makes it much better for the particular point we care about, which is the one we're making a prediction for. It's a bit surprising because it's a single data point, and maybe you have trained with 1 million data points. So the question is, why does that one data point matter if we've trained with 1 million data points? Well, the idea is that you're training on the exact point you care about. So enforcing the inductive bias in the exact point you care about right now, for which you're making the prediction, is going to have a very big impact. And so in this case, this gradient step improves the prediction just for that one point.
Yeah, maybe it's also important to highlight that the parameter here, this theta that we start with, and also the parameters of G, those are the ones that will be learned during the training procedure across the entire training data set. And then the parameters here, those are always constructed in the moment, data point by data point,
exactly,
to as you say, tailor the inductive bias. And the inductive bias in this case would sort of be this entire term right here.
Exactly.
Essentially says, how do I need to change my predictor in order to conserve the particular thing that G decides is the common quantity for this data point.
Yeah.
And this gives rise to the algorithm. So here is what we just discussed. This is the forward prediction sequence with this inner optimization step. So we first predict this plane sequence, then we temporarily update the parameters, and that allows us to again do the forward pass, but now with the updated f function, and that gives us sort of our final predictions. And as you can see here, during the training, we sample always batches, we forward predict using this inner update, and then we take outer gradients. And the L task here, that would just be what you call the task loss. This would be the video prediction loss. Exactly. Or something like this. Okay. So I have a lot of questions. First of all, it seems quite intricate, right? Because if I think, okay, these outer gradients right here, especially this gradient right here, this is how do I need to change theta? Now, okay, how do I need to change theta? This depends on these predictions right here. These predictions right here have one forward pass using theta, then have a gradient with respect to theta right here inside of them, right? Yeah. And all of those come from this quantity, which is already a forward pass using theta, right? Yeah. Is this actually how it's implemented in practice? Do you do stop gradient somewhere? Do you have any hacks? Or is this actually, because it seems mighty unstable, right? How does this actually work as you specify?
Okay, yeah, that's a good question. So in general, it depends. So if it was a single prediction, so if it was like the default, sometimes we've applied this kind of prediction time optimization, the tailoring procedure to regular tasks like image classification and things like this. It's not that unstable because you're just kind of doubling the computation graph because you make one prediction and then gradient step and then double that prediction. So that's fine. Now here you have two issues: the fact that you're taking the gradient step and the fact that you have many predictions that kind of build upon the other. So that could get tricky. In practice, we've seen that if the overall training regime is stable, then it works fine. But if the overall thing is already unstable, then it's extremely tricky to add things there. So for instance, one thing we realized was that because video prediction is very expensive, and basically we couldn't fit that many examples on a GPU, literally I think 2 or 4. So we were initially using batch normalization, and so that was making the vanilla training of the vanilla neural network, so just F, already unstable. And when we were adding our Noether network improvement on top of it, it couldn't learn anything. When we swapped the batch normalization for layer normalization, then the vanilla training was very, very stable. And then suddenly the Noether networks worked out of the box. And we think that that's because if the original gradients, because of the batch normalization, if you compute the batch statistics with a very small batch, it's already very crazy unstable. And then we couldn't learn. When the other thing is already stable, then it seems for us it worked pretty out of the box when we swapped the layer normalization.
Okay, that sounds good. Yeah, I would expect so.
Yeah. So for instance, I would expect, for instance, if we were to do 100 steps or many more steps, or for instance, we were discussing before how there were two losses, that sometimes we tried one or the other. The reason we came up with the second loss that conserves kind of the conserved quantity between this time step and the next time step was when we were using batch normalization, and we were wondering, is our Noether network unstable? And then we realized, okay, no, it's the vanilla network that was unstable. But that was part of our concern, because there is some papers that mention that when you're backpropagating through a very deep graph, then the gradients are sometimes not very informative. In our case, we found that when the thing is pretty stable, seems to work fine. But I could expect that if you make very, very long predictions or your thing is already unstable, then it only adds to the instability, taking the second order.
Yeah. Yeah, and another thing that struck me is that there's only one gradient step here. You take one gradient step, and I'm going to, that might also be something where stability or computational graph size. First of all, you just do a gradient step. Many things would be possible, right? You could do an Adagrad step, you could do an Adam step, you could do a line search or a Newton step or anything like this, but you have chosen to do like the most simple thing, which is a single gradient step, right?
I think the key word here is what you said about simple. We could have done anything else, but I think simplicity is something to value a lot in research, I feel. And so we went for the simplest thing. And so one gradient step. And if you can train with 3 gradient steps, and we've sometimes done that, it's a bit better because this allows you to take smaller gradient steps, and then sometimes you optimize the inner loss better. But in terms of one, simplicity, if it works with one, it's better. And 2, especially when you present the algorithm in a paper, you really want to show the simplest version, and then usually people now know that, okay, if you can take one gradient step, you can usually take more than one gradient step, and it will just make the computation graph larger, but that's fine. So we were striving for simplicity both when we were implementing and then when we were showing the algorithm.
And you do have experiments that show that even though you learn with one gradient step, and that is down here somewhere, even though you learn with one gradient step, you can, in fact, at inference time, then perform more than one gradient step, and that up to a sizable amount of steps, like up to 100 steps or so here, will actually improve the outer loss, right?
Yes. We think that essentially the Noether loss is kind of a projection loss, right? Because you keep saying, okay, why don't you make G happier and happier? And especially in the theory section, we go a bit about this, but essentially there is many futures you could have predicted, and some of them make G higher. Imagine it's only one quantity for now. Some of them will make G higher, some of them will make G lower. And when you force to conserve G, all these features say, okay, no, you should conserve G, and therefore it's kind of projecting one dimension. And so in particular for conserved quantities, applying the same laws over and over, it's kind of stable because you will just keep going closer to this manifold of predictions that conserve G.
Yeah. So there's no let's say danger of overdoing. I mean, there's a little bit, but as I said, it hits after like 100 steps, which is quite a bit, right? Given that you train with one.
Yes. So eventually, especially because also these are neural networks, so it's not like it's for instance, we've tried with this with hard-coded losses in the previous tailoring paper, and it's the true conserved quantity and the energy is truly conserved, then you can freely do that, and it will keep going down. But because it's a neural network, then suddenly I think you're going outside. It's kind of a distribution shift. You train G to be useful for 1 or 2 or 3 gradient steps. Now you're using it for 100. It doesn't make you any promises.
That makes sense. Now, so I wanted to also come back a little bit to a more conceptual idea. Maybe this is also a bit of a question about tailoring in general, what you do here, that you essentially adjust the parameters of your forward predictor on the fly. There are many ways you could have combined the two networks, right? The one network that essentially predicts the conserved quantity and the other one that forward predicts. For example, you could have optimized the predictions themselves at runtime to make both of them happy. You could have, I don't know, you could have just learned it as one thing and not even bothered with runtime optimization. Why did you choose this tailoring approach in particular? It seems a bit cumbersome, right? And it's not maybe the first choice one would come up with. What are the advantages here?
So there's 2 things in your question. Let me answer one after the other. So there is one, why the prediction time procedure, the runtime procedure, and then the other one is why adapt theta instead of x. So let me start why the runtime procedure. It goes back to what we were talking a bit like 10 minutes ago or so. The fact that the alternative to tailoring is auxiliary losses, which are, you could say, okay, we are going to learn an auxiliary loss that is going to be helpful for the final prediction. So there's 2 points here that I think could be improved. The first one is we are trying to learn an inductive bias. For instance, one very cool thing about Hamiltonian neural networks or CNNs or transformers is that the inductive bias that they encode into the network applies at training time, but also applies at test time. So you know that you have equivariance at test time. And you know that your prediction satisfies this inductive bias. And so auxiliary losses, if you train for energy conservation or whatever loss you want, do not satisfy the inductive bias. And so for it to be a proper inductive bias, it has to be satisfied also at test time, and that's why we optimize it at runtime. You also have to optimize it at training time, because if you optimize it only at test time, then you have a distribution shift. So that's why it has to be optimized inside the prediction function. So that's the first reason why. To be a proper inductive bias, it has to be optimized at runtime. The second question was, and there's a second reason why we also do that instead of auxiliary losses. The reason is that there is a very immediate signal. So imagine you encode energy conservation. At training time, then it's a very loose signal to the final test prediction, because you're saying, okay, this is going to affect my final training parameters, and then I'm going to use my training parameters on a validation set, and this is going to lead me to good predictions. But this is only happens, you only can look at the effect at the very end of training, and then you're going to use that on validation. And so you could do that, and I think there's papers that do that using implicit gradients, but the signal is much more cumbersome. Instead, if you say, okay, no, the way I'm optimizing this is inside the prediction function, then you can literally compute the computation graph and optimize it end to end. So that's the reason why we do that at runtime. Okay, second point in your question was why theta and not x? And that's a great question as well. On that, we experimentally found it a very impactful, very stark difference between both options in the tailoring paper. And we think we understand why. The intuition is optimizing x actually helps. Experimentally, it makes sense that it helps, and it also empirically found that it helps. But it helps very little. The reason being that you can, it may find like an adversarial example that optimizes G perfectly and makes G very happy with very small changes. If you optimize theta instead, theta has kind of the geometry of the task. It knows the ways that the ways to change the output conditional on the input that kind of still do not deviate too much from what it has learned. So theta captures the dynamics and says, okay, I probably got it a bit wrong because I'm not conserving G. But I don't want to deviate too much from what I've learned. So optimizing theta still make sure that you satisfied what you've learned so far, and then it leads to much larger improvements.
Yes. I mean, it does bring up, like, just right now, it does seem like might be possible to set up some adversarial setting right here where you could maybe use G as sort of a discriminator, not optimizing X directly, but sort of optimizing the parameters of F in maybe more of an adversarial setting. So not directly taking a gradient step with respect to the loss, but maybe saying, is according to what G outputs, is this a real sample or is it a sample that I have predicted? Is this anything on your radar? Or
I think it's I think there's something like what you said that's going to be there. In particular, I think G has a feeling like this adversarial discriminator, because it's telling you, oh, if you're not satisfying G conservation, then most likely you are wrong, especially if you don't satisfy it by a large amount, because again they're approximately conserved. So that's one. So one thing I'm interested in going forward, and I think that could be a avenue of many future works, is that we focused a lot on when we're trying to make predictions on kind of generative networks. The fact that generative not in the sense of self-supervised learning, but more in like you predict the next input given the output given the input. You have to generate the thing. G is like a checking network, and checking sometimes is easier, right? You just have to say stand back and say, okay, I like it, I don't like it, and that may be much easier to do. And also the type of network that you have that you build in may be very different architecturally. Maybe the type of networks that we want to encode and construct may be architecturally different from the F networks. And maybe combining these proposal networks with these checking networks may make different architecture classes that could be useful.
Yeah, I wanted to get a little bit more into, so you have experimental results where you compare to various baselines, like, without and obviously you're better than them, which is what we've come to expect from machine learning papers. I wanna focus a little bit on also, here you have an investigation into what the conservation, what the embedding network, this G network, actually looks at. Do you maybe want to comment on this a little bit, and why this makes you comfortable saying, like, comparing this to conserving quantities, and why your assumptions might be correct?
Yeah. So we were able to check the fact that we were learning conserved quantities in two ways. One, the symbolic experiments on the physics based, we were able to recover energies, but in the video it's very hard to know, are you learning anything meaningful? And so we were able, okay, let's inspect what the G network is looking at. One thing here, just to be precise, is that we have to, it's a dynamical system, so we have to have some notion of velocity. So G was actually taking 2 consecutive frames to be able to have any chance of visualizing the velocity. But here, okay, we only look at one of the frames and we say, okay, where is it looking at? And if it's not looking at this reasonable stuff, then maybe it's not doing anything. And so if you look at the Noether laws, it's an MSE of multiple dimensions. In our case, we tried, that hyperparameter didn't really matter for experimentally. I'll come back to this a bit later. But let's say we fixed it to 64. So it was predicting 64 numbers. But you can, if you think about it, you can kind of rotate and exchange the dimensions and whatnot. So really what matters only is the PCA of this. So you can take the PCA and look at what's the most important dimensions, and then kind of at the least important. And we found that even though we were trying to conserve 64 different numbers, in practice there were only 4 to 6 that mattered. And in particular, the first one mattered a lot. I think 84% of the variance was captured by the first dimension. So it's the one on the left. And it was comforting to see that this dimension was looking at the right stuff. So in particular, it looks primarily at the object that's falling down. You can see it in red. And then we also saw that it was often looking at the edge. We think that this is because there were 2 types of, here they're both right to left, but there were sometimes sequences that the object was falling left to right. So we think that the edge of the ramp was a good signal on measuring this. And it also looks very faintly, but it also looks at a bit at the object waiting to be hit. So that was very comforting to see. So you can see, for instance, other dimensions that were much less important than the first one. They are not very meaningful at all. And then the fourth one and the sixth one do have some meaning. We think that the fourth one was caring more about orange type stuff, and we think that maybe it's because of there was sometimes a hand that was going on there. We don't know. And the sixth one, we found that it was following blue objects very closely. So here, of course, we only show one example over time. So this is the time sequence as we track the object. On the appendix, we show that it basically didn't matter. The example didn't matter. It reproduced very nicely. And that also gave us confidence that the G network was learning something meaningful.
Cool. So I have this question. You have a lot of these physics examples, right? Which also comes close to your notion of, in physical systems, in dynamical systems, there are these conserved quantities and so on. Is it fair to say that probably in most video prediction tasks, unless it's like, I don't know, a SpongeBob video where every 4 seconds there is a cut, like in most video prediction tasks, I can reasonably say if a model just observes the pixel information, then probably it's going to find some of these conserved things. It's almost like a prior on, stuff over time moves slowly and in according to physical reality or something like this.
Yeah, exactly. I think there's probably some type of prior like this that enforcing the fact that some things are approximately conserved is going to be useful beyond physics. It's true that we've, because of the motivation especially, we thought that that's the most likely thing to work, and also the message was clear. But we think that possibly in other types of videos, even like many videos are essentially everything is physics. If you're in the real world, like cars or people moving around.
Yeah.
But they also have some intrinsic movement that doesn't follow passive physics laws. But there's always
do you have like something in mind, like except cuts between scenes?
You'll get goodbye.
Yeah. do you have anything other in? Is there like a prominent example where this type of model would fail?
So I think let me think.
I mean, I was thinking maybe.
Yes, I know.
So go ahead.
One easy example of something that would fail is you have a video and you often have things that enter the video that were not in the video.
Yeah.
Then here you get into trouble because there's something that was not observed. It's the same thing that we were talking energy dissipation before. If you consider the entire system, then maybe there's something that's going to get conserved if you consider heat and whatnot.
Yeah.
But anything that you cannot observe, then enforces some things that are not getting conserved. So extra objects that appear and disappear, then you're going to get into trouble.
Yeah, I was like going to mention the exact same thing, and I mean it's still going to be the case that the G network, it can just output something like, well, the energy of the entire universe is still the same, right? But that then ceases to be useful.
Yes, exactly. So things, and one other thing, I think conversely, it could be that there's a lot of work that will need to be done if the camera is moving a lot, because then all of these objects will for sure appear that were not there, because you're looking at stuff that was not there. So if you look at the videos, this video is static. The camera is static. Sorry, the scene is not static, but most likely some work will need to be done in this case. One good thing about this is that we're not fully imposing the conservation. Some approximately, actually, the fact that it's approximate allows us to handle things that were not previously possible before, but still you will get into trouble if you keep entering stuff.
But it's, I mean, just out of intuition, it seems more likely that the network detects something like, there's a blue bunch of pixels and an orange bunch of pixels, and these pixels sort of move together as objects, rather than the network from video somehow determining, there's laws of physics and there's gravity and there's friction and there's sliding. The first situation seems a bit more likely here, right?
Yes. Actually, so just to, for instance, give a bit of context of how we came up with this idea. Initially, the original tailoring paper, we initially came up with applications on adversarial examples and contrastive learning. And I had the feeling that it could be applied to inductive biases, but I was not fully sure. I didn't know exactly how. And then the Rusted Ray gave a talk at MIT. It's online on the YouTube EI seminar. And it was telling us how it's very hard to encode inductive biases in neural networks. And in their case, basically, they were predicting how a robot was pushing a bunch of carrot, and the carrot was moving around, and they trained it. They trained a carrot predictor, and that it worked fine, very good prediction. But then they used it for planning at test time, and suddenly it was not conserving carrot. It was making carrot disappear instead of bringing it to the proper place. And they were like, okay, that neural networks don't work, so we're going to use a constrained linear model. And they were able to solve the problem this way. But I was like, okay, maybe we can actually, if we enforced it inside the prediction function, it would conserve carrot. And then that was the motivation that let us go into this direction.
Cool. Is there anything else you want to say about the experimental results? We touched on sort of upping the inner steps and the grad chem, But is there anything special you want to say about sort of your tests on, for example, the pendulums or?
Yeah, I think some of the experiments, it depends on how much time we have, but on the pendulum, there was a symbolic component, so the G doesn't have to be fully neural.
Yeah.
So in the first, I think those are the first experiments, the G is kind of a program with some parameter, like a formula. And there we search over formulas because it's a state information, the pendulum that you draw, like the angle and the momentum. And there we search over formulas. And then there's some parameters as well that get trained over with gradient descent.
Yeah.
And there we saw that, okay, we are able to recover the true formulas of the energy, and it leads to better prediction than a vanilla MLP that does not learn about conservations.
And there also you can see that actually you can even handle these approximate constraints where you have real data, which then the networks that have the hard-coded constraints can't handle as well.
Yeah, exactly. So there is a cool paper, Hamiltonian neural networks, that encodes, I think the graph is a bit above, I think, that basically, this one, perfect. So it's a very cool paper that they construct the network in such a way that it conserves energy. And so we thought it was a very good comparison because it improves a lot the above a vanilla MLP that does not conserve energy. So if you look on the right, this is changing HNN conserved quantity, which is what they believe is they predict it's going to be some of the energy. You can see the baseline neural network, which is just the F, basically, just F, quickly loses energy, and therefore this is going to lead to much worse predictions. On the left, you can see the MSE goes up. If you fully impose energy, well, this is a much better inductive bias, the fact that energy is conserved, and you can see that the predictions are much better. But if you only softly encode it, then we show that we can do much better. And then we compare to actually knowing the loss, the formula for the energy, and we see that essentially the performance is pretty much the same. We are able to discover it and then use it to softly encode energy conservation.
Nice. Seems like a good deal. I mean, it's really cool that if you know something about your problem, this is sort of another way that you can directly encode that, even in sort of a soft way. I think the softness is something super useful, especially in the real world, right? Compared to sort of the really hard constraints that often these symmetry conserving neural networks have.
Yeah, exactly.
Cool. Yeah, I think this is about it for this paper. Is there anything you want to, you have a theoretical section. We didn't talk much about the symbolic regression, but I think we've gotten sort of to the essence. Is there anything else you want to add to this or anything people should know? That your code is online, right?
The code is online, so it can be easily built upon. It's on with PyTorch, but I think actually JAX will make it these type of things of parameter kind of this tailoring process that essentially you have a parameter per example with JAX are it's very easy to encode and parallelize, so that will also make it easier. But with PyTorch it's already pretty easy with PyTorch higher it's very easy to implement. So I think that should be easy to build upon. I just wanted to point out that this was a group effort. So in particular, Dylan Doblar was also a first author in this work. And did a lot of the experiments. And then we also had Alan Cho and Chelsea Finn from Stanford collaborating on this work because we found they had a really cool paper on learning discrete symmetries, meta-learning symmetries by reparameterization. And then we also had Professor Josh Tenenbaum from MIT Cognitive Science and Kenji Kawaguchi from the University of Singapore.
Cool. Excellent. Well, Ferran, thank you so much for being here with us today, and all the best. I hope you have great ideas in the future.
Thank you.